Hi, this video is about divergence theorem. In the earlier part, we talked about Green's theorem and Stokes' theorem as a kind of a generalization. But this divergence theorem can be viewed as a different direction of a generalization, truly higher dimensional version. Even though it looks like a higher dimensional analog of as well, if you think about the Green's theorem to the Stokes' theorem, it is just changing the way the ambient space is sitting in. So it is intrinsically, it's not the higher dimensional version. But Green's theorem to divergence theorem is a higher dimensional version. So let me use picture to explain this one. Think about Green's theorem. This is a 2D, two-dimensional space. There happened to be a nice curve that the curve itself happened to create this region D. And there's oriented curve C. So line integral of a certain vector field or any vector field that changes to double integral over xy plane. That's the key thing in here. The true analog in here is that this curve is really high. The higher dimensional version of that curve is a surface. Think about its bubble soap. That's a surface. And this surface does not have an edge. Because of that, Stokes' theorem does not directly apply. But we can kind of think about this surface integral situation. So it kind of applies, but that's not what the Stokes' theorem is truly about. So that's a 3D, and there's this bubble soap. It's there, and you can think about all the air that's filled in there. Instantly, you can change that air to something solid and think about this whole thing as a solid W inside. And S is denoting just the surface part. Then we think about the line integral here. The true higher dimensional analog will be surface integral. This is not double integral. It's a surface integral in three-dimensional space. But intrinsically, it's still 2D object we're handling there. And that is becoming, here it's a double integral, truly in three-dimensional space. That's a triple integral. So that's a double integral dr involved in there, surface integral and dn, the normal vector multiplied. This is a double integral, and there's a triple integral. There's no vector field involved in this double integral and triple integral. They're truly just a standard integral in the flat space. So in that way, truly, this is a higher dimensional analog. However, there is still something different about. You will see that even though that's kind of the setting, the difference here is that what we are dotting in here, we're dotting with this kind of tangent line vector in there. Here we're not dotting with anything tangent. We're actually dotting with normal vector, right? Not tangent to the surface. So that's a slightly different. Because of that, the shape of the expression you inside the triple integral and you see in the Green's theorem is a slightly different. Slightly negated, twisted version simply because of this tangent versus perpendicular. In the simplest term, just like a negative reciprocal when you look at two lines that are perpendicular to each other. Okay, so let's enter the context in the theorem. Just like before, because we want to write down, as rigorous proof and want to make the proof as rigorous as possible. Hold on, I did something wrong. I'm back. We have to assume that there is a solid and there is a boundary, and they must satisfy a nice property such that it can be broken into pieces into over xy plane, on over yz plane, over zx plane, all that, just like we did to the Green's theorem, we did it over xy, x-axis and y-axis. So that's going to be the nice part, and enclosed part will be is going to be the surface of a solid, so it's not going to be like an edge. For example, if you draw a little loop in the space, this is 3D picture, and then you can fill in between with a flat surface, just like a disk sitting in, hovering in the three-dimensional space. In that case, we have an edge. And you can see this surface itself doesn't quite form any solid. But if you think about cube in three-dimensional space, or an ellipsoid, or a sphere, and if you think about the surfaces out there, it kind of closes up, and there's no edges like that. You might call this one as like a sharp edges, but it is still, there's no end to the surface. It continues to the next surface and stuff like that. So that edge is not the edge you're talking about in here. It's like an end of the surface. It's not end. You can just continue it like that. And you can see as you walk around the surface, there's no end to the surface. So that's closed surface we're talking about. These are the closed surface, and this, disk with edges is not closed surface. So especially looking at this type of solid and the surrounding surface and its outward, then again, outward orientation is what we have in here. So because we're doing the dot product, orientation is important. If you have a solid like that, if you look at this piece of a surface, for example, then we're orienting this one to that, for that surface integral. That's why we need that orientation. This is quite clear and naturally continued everywhere. So it's outward orientation. So with that much of orientation in the thing, then we can enter the statement, but we still have to describe that projection property so that we can handle it nicely. So here it is. If you have a solid, we should be able to project it down over, for example, xy axis, such that there is this region, and for that each of this point in that here, there should be 2 points above here, one from the, coming from the kind of lower part of the solid and the top part of the solid. And you shouldn't, bump into 2 different points in between. For example, if you happen to be looking at, even though it's a 2D picture, you can imagine, like this one little ball, then this is the projected image down there. And if you put a point down there, you can see there's a multiple points up there. We want to make sure that there's a lowest point, there's a highest point in between. We can just go through quick, when solid, everything in between must be part of the solid, not like this hollow in here, non-convex version. So we want to avoid that kind of thing. Make it simple for every direction. So you can write that kind of thing mathematically like this. Its projection, all the points in solid projection down to xy plane must form this nice region so that we can apply Green's theorem to that. That's one thing. And over that each point, there is this lower bound and there's an upper bound. Everything in between must be the points in the solid. It should be constructed in that way. So in that case, we can just play with this, functions, and then we can enter two-dimensional version. So you can see because it's, because of this projection property, we can break it into two-dimensional pieces. The same thing in here. If you look at this YZ plane, the projection must form a nice region so that we can apply Green's theorem and stuff like that. And from there should be a lowest bound for, this is x-axis, x, and upper bound there. And every point in between must be part of the solid. And lastly, and if you look at ZX, and this is a ZX plane, if you look at that same nice region so that you can apply Green's theorem again. And everything in between with this y coordinate lower bound and upper bound, they all should be in there. So if that's possible, then we can do this analysis. If it is not, then like we did it before, you have to break it into different pieces and apply these individually, and which is, in generality, it's an interesting problem, but it is a simple application of that. But that doesn't mean it's easy. So here is the statement, left-hand side, like I said before, it's the surface integral. So there is this dot product going on, and right-hand side, and you go to a higher, level of integration. Now it becomes not a vector field integration. This becomes just a triple integral. That's not double integral. That's a surface integral of a vector field. Here's a triple integral. And again, the phenomenon is captured at something called the divergence operator. So if you have a vector field at PQR, I'm not sure if I wrote down anywhere up there. There it is. There's PQR in there. Then this divergence of F is particularly simple and nice to remember. That's why it's slightly different from the Green's theorem here that says x component differentiated with respect to x, y component q of the vector field differentiated with respect to y, z component of the vector field differentiated with respect to z. There's no, twisting around, so it's so easy to remember, and slightly different from Green's theorem. It has to be twisted around and negative and all that. Again, the quick answer to why does it look different is that Green's theorem is dotting to the tangent vector, but surface integral is dotting to this object, like the surface, we're dotting to the normal vector. That's why it turns out a little bit different. So it seems like normal vector is more natural. There's no twisting going on. So this more natural thing to actually consider. You probably felt that when you learned the gradient vector and how it relates to find the equation of a tangent plane or something like that. You realize, oh, this is actually the right object to look at because math turns out very symmetrically and pleasing to our eyes. Like in the Green's theorem case, the operator was a curl operator. If you do that curl operator and you arrive it in here kind of higher integration level, and if that operator becomes zero, the same thing we're assuming. If that happened, that after differentiating like this whole thing cancel out or individually zero. If the divergence is zero, that means this whole thing is going to be zero no matter what your solid is. So that makes this surface integral zero. So if you look at kind of nice bubbly soap in there, and if this surface integral measures how many things are going through that surface area, like a number of particles, that's how I motivated the surface integral. And then it means it's a zero. That means, going out, because it's outward oriented, and positive number that picks up a certain portion of the surface integral. That means they're going out. And because it's zero, that means that something is coming inside. So for example, if I have a sphere in that, if the particles are moving to that direction, of course, that is our normal vector. Then because it's in the same direction, that kind of measures, this is going to measure how many things are going out. And this is oriented like that. In that neighborhood, if the particles are going through that, it's going the opposite direction. So that's going to count it as a negative number. So all together, all around, how many going out and how many going in, altogether it turns out to be zero. That's what this one's measuring. So if you think about imaginary kind of bubbly soap in there, and there's just air particles just going through like that, and think about it, if inside this the region, the number of air molecules are staying the same, that means going out and coming in is exactly the same, and that's exactly what you expect. Unless there's a sink or something like that, such that it disappears into somewhere else. Other than that, it's going to be always the same. So it is kind of capturing that kind of phenomena. So if that vector field flow happened to have a divergence to zero, then it is capturing that phenomena. Everything, number particle inside, in and out together, is going to be zero. There's no change. That's what it means. There's a similar application, just like we did that before. If we have a closed curve, we broke it into two pieces and realize that there's a path independence phenomena. Remember that part? Let me go ahead and make that connection. Because this Green's theorem, if the curl is zero, this whole thing is going to be zero. If it is closed loop, you're going to have an integral that is going to be zero, just like that. But if you do it in an opposite direction, that means the value of integral through that, value of integral through that must be the same, such that this happens. And that gives you a surprising result. It doesn't matter how you get there, it's going to be always the same if the curl is 0. Kind of the same phenomenon is happening here. If you break that closed surface into two pieces along this um, boundaries which is introduced here, and here if you look at the curve, closed curve, you can just two of this point. That's a beginning and an end point. It's kind of the same. You go ahead and make your own choice of this curve, and you're going to have some surface above it, some surface below it in our context, the simplified context. And you give the same orientation. And if you give the orientation upward in here, and also orientation upward there, that's how this surface integral is for example, Stokes' theorem, usually that it's formulated. So if you integrate positively using right-hand rule to that S2, that's not the same orientation you see when you're putting together into a solid. So that's supposed to be, downward, outward, and here it's a downward, but that's not, following the right-hand rule. Right-hand rule to the second piece there, thumb is up. So that should be the correct one. So if you compare these two integral with the same orientation with the curve and all that, so it has to be opposite there, then they cancel out because that switches the outward to upward orientation there, so they cancel out. So it doesn't matter as long as you have, so let's put the context a little bit different. Before there was a solid, and then we cut it out there, but let's look at it slightly different. If you happen to have any closed curve in here sitting in three-dimensional space, and you can create any type of a surface that is oriented positively along that curve, and the same curve, let me go ahead and try to copy as similar as possible. Let's see, let me make it really big, like this, crazy big like that, right? Then this whole thing is going to be the same. It doesn't matter how you actually put them together. It's going to be the same solid as you orient it different way. So this is kind of weird. Let me go ahead and change it downward and explain this one later because this is a little confusing in there. So if I happen to choose, let's say this, it looks like nicer, like a kind of flat one, as flatly as possible. Because of the curve, it's not possible to make it flat, but as minimal as possible. That calls a minimal surface. So if you put them, so this is upward according to your right hand rule. If you put them together and glue along this, boundary, as you can see that bubbly thing in there, and there was this edge before, but we close up with this surface in there. Not it becomes a solid in the surface. And because it's supposed to be oriented outwards for that surface integral, but we're oriented upward, so putting it together, they cancel out, and this is supposed to be 0. That because we're looking at divergence 0 vector field F in there, the surface integral along this one with opposite orientation, let's say the surface, this is going to be 0 when you do dn there. All right. So because of that, if you put an opposite there, this integral and that integral is the same. So before, in the line integral situation from the Green's theorem, if you go around like this, go around like that, if the curl is 0, this is going to be the same. Total surprise. And here, the situation is if your divergence is a 0, you're looking at a vector field, if your divergence is a 0, and if you're looking at this curve, which is corresponding to this point, if you choose this curve, it doesn't matter what kind of surface you put it around it, this crazy one and the simplest one like that, that surface integral is going to be S1 dn is going to be always the same. I wrote it here. Let me write it there. So let's look at it slightly different order. If you have a curve, and doesn't matter what kind of surface you put it in there, it's going to be the same. The surface integral will be the same. So let me go back to that crazy picture that I wasn't able to um, explain to you. So let's say that was a surface C and oriented like that, and there's this big one in there. I'm going to have the same surface in there, but in there, there's a little hollow in there. That's how they put it together if you look at it in the same upward. Again, so that's orientation this way and orientation downward, and that's the same situation because of that. It happens there. So they call this a path independence. I don't know what to call this one. Never seen people calling this one. Is a surface independence. Maybe you should call that. It doesn't matter what kind of surface you put it in there for that boundary. The integral is going to be the same always. If your vector field has this interesting property called divergence, vanishing divergence. So this is a typical example I was using before. If this function does not have x component, this middle function is independent of y, the last one independent of z. What is a divergence? Derivative with respect to x, derivative with respect to y, with respect to z. And this is not vector. That's another interesting part. This is going to be scalar function. It's a 0 plus 0, not 0 comma 0 comma 0. So divergence is 0 anyway. So this type of function will have this divergence part, 0. And another interesting part is this. The standard example of the vanishing curl, therefore you have a conservative property of line integral, that was a gradient vector field. So what kind of the vector field has a surface integral 0 and divergence 0? What kind of field is that? Its curl is a main example, right? Starting from the scalar function, the gradient vector gives you this conservative property, a conservation property, and you can think about it saying, what kind of thing has a conservation property? If you go around the surface integral 0, it is the curl vector field, the vector field that happened to be curl of other vector field, right? So in that case, it turns out it's a divergence is 0. So let's see why that is so. This is a curl with a part ABC. That is the vector field we're integrating on the surface integrals. Don't get confused. This is not the Green's theorem, it's a higher up version. So we're looking at the vector field and doing the curl, and we're doing the divergence to that one, right? To see this has a divergence 0. Not sure if I'm doing that here or not. I think I'm doing it there. Down here, divergence theorem states this. I'm calculating divergence in here. So this is really easy. This x component differentiated with respect to x. So I'm putting the x right next to it. This az and y next to it. Bx minus ay differentiated with respect to z. So there's a z components to it there. Just like that. So you can see the CYX appears as a CXY again to Clairaut's theorem. They cancel each other. BZX and the BXC, they cancel each other. And CXY, that is a CYX over there. I think I did that one. Whatever I didn't do. AZY with the AYZ, they cancel out each other. So you can see that the divergence is 0. And because of that, and this surface integral is going to be always a 0. And I probably have that statement below. This is pretty much it. All the vector field that has this property that the surface integral is always 0 must be locally curl of something. But you cannot say globally. And that's where it gets really interesting. So here I wrote there. If you happen to be looking at, so I summarize it, if your vector field happened to be a curl of something, and then that your surface integral is 0. And if your surface integral happened to have this property that always 0 for all kinds of, this forgot to write down the quantifier in here, all kinds of closed surface, if it happens to be 0, that is locally, that makes a divergence 0 because it's all condition. It's not just any surface, any closed surface, that makes a divergence 0. And if the divergence is 0, you can conclude that locally that it's a curl of something. But if you try to extend this formula all the way to the bigger one, especially something that closes up, and you're gonna run into trouble, and it's not always possible. Sometimes it's possible. So let's think about the proof. Proof is very similar to the Green's theorem. You look at top curve and bottom curve. Here you have to look at top surface and the bottom surface. We did something like that in Stokes' theorem as well. We only have top curve, so one curve there, one surface there, and so two surface you have to put in there. Because everything in between here is a solid, and we assume everything is vector field is nicely defined there, and you can turn that difference in there. You will see as you change the boundary, you can put that into a iterated integral. That's where we get this triple integral pop in. So first you look at the, this surface integral, break that into two pieces, this top piece and the bottom piece, and parameterize it with a two variable. That makes everything the double integral. So there's this top piece S32, S31 down there, but it has the different orientation. So if you have that curve also, to assume that there's a curve involved in there with the boundary of that thing there. So this is going to be changing to negative because just with that surface of the curve over there, we want to change it, oriented into right-hand rule. So we change that direction of this orientation. That causes negative, and that's where iterated integral kicks in, something minus something, when you do antiderivative. Right, let's think about how to unfold the surface integral to double integral, right? You've got to have a parameter. In this case, that parameter is x and y. Usually, in general, it's s and t. And this dn, the dot product dn in the surface integral, changes to your parameterization of x and y and the cross product, right? And that changes to double integral like that. So you got to have a parameterization. This parameterization of this surface S2 is given by this formula in here, right? So because it's Monge parameterization over xy, we already calculate this normal vector from the Stokes theorem. So here it is. That's our RS cross RT. Here's RX cross RT, and that's a negative ZX and negative ZY differentiated. This is not the square. It's just a notation I have to use. So this is the index. All right. It's a top function and bottom function in there. So this is a top function F2 and differentiated with respect. That's the normal vector. And here's the vector in there. And the other one has to be upward like that. So that's the same thing, I think, there. But because of this different orientation down there, oriented downward, using has to be opposite sign, and that'll do it. That's a normal vector upward. If you just put the negative, it's going to be upward vector. Down here is a downward. So if you negate it, it becomes upward. Okay, so that's a direct translation, changing the surface integral to double integral using parameterization. Now in the next part, I focus only on the z component. This has a PQR. There's no derivative involved, but z is composed like this. So that's nice. That's all the parameterization. So that's not as complicated as the Stokes theorem we've seen before. So if you focus on z component, there's r, right? And multiply by 1, so that's nothing else multiplied. And this z component now has f2, that's upper part. If you look at it here, if you look at r component, that's negative, so negative out there, and it's r, where the z component is coming from the bottom parameterization. So there's negative and on that. So if you look at it here, that's exactly this one minus that you see when you calculate antiderivative. So you can put that one into x and y given fixed, when only z part is changing. So you differentiate with respect to z and put that bracket. That's the same as integral for z part only where x and y are fixed. All right, here it is. That's exactly, I was wrong about RZ part. I have to cross that out. I don't know. I think I might be able to do that. Go ahead and fix that. All right, I think I patched up. So you do not need a z derivative in there. Just a r, you plug in f2 in the z slot and f1 in the slot subtracted. That's what we had before. Now, if you put that into a one variable integral, then you have to differentiate for z and then put the limit bound in there. So I hope you see this is kind of cylinder coordinate integral, right? So that's natural. That one captures the volume over dxy. So it's probably that out in there. So I hope that the connection is simple. Think about these triple integral and how you're going to calculate the triple integral if this w has this nice projection over xy, and then given xy point, you go through from the bottom to the top part. If everything in between is a part of the solid, this is exactly how you would calculate these triple integral, right? So backward is kind of awkward, but if you think about how you're going to calculate this triple integral, this is the first thing you probably are going to do. So this direction is easy. It's just like expanding a plus b squared is easier than factoring a squared plus 2ab plus b squared, right? So it's just interesting enough. It's just happened with completely isolated. There's no mixture of an x and y multiplied. So what is left out there is just the p and q. R is all gone in there and completely changed. So I rewrote it there. That we have calculated here is a triple integral, RZ. And what we have used before, we just use this R multiplied in there. So R is gone. So why don't we change that to 0? And I hope you see that's exactly the same. If you multiply this one there, like that, R, then R is there. And the remaining part is P multiplied there, Q multiplied there. And 0 is all gone in there. So I can write it like this and look at this as it's the same thing before. Now you have a vector field PQR. Now you're doing this surface integral with a vector field PQ only, all right? So the same vector, but we didn't put any special condition on the vector field. Vector field can be anything. It is just about the surface condition. Now to take care of a Q, you look at this as a new vector field. You do exactly the same argument. Trace this one, put that back in there. So let me go ahead and write that. Back in there, this the original surface integral. That surface integral S, we have broken into two pieces like that. Put that back in there. And what we're seeing there, we now have a new vector field against to that. So I hope you see that you can go from there to that one back. And then this time, this is going to be broken into different direction of pieces. And then that takes care of Q part. Hope you see the exact symmetry. And once this Q is gone with this type of thing, the triple integral, the remaining part of the vector field is going to be P0, 0, and put them back together and look at the surface integral, look at the different direction, and then break that into three parts, and then you're going to pick up px there. I think that's what I probably write there. So it seems like I'm skipping that whole explanation in here. I'm using other projections. The calculation goes exactly the same. The key thing is that you make an observation. After you do this calculation, these things can be put back into this shape again where our part is just missing. Right, next video is going to be the shorter one. It just compares the Green's theorem and divergence theorem. And like I said before, why is that negative is involved in the Green's theorem and divergence theorem is not. Again, it's because we're dotting against a normal vector and where Green's theorem is dotting against this one of the tangent vector. That's the difference. So in the next video, I'm going to consider not Green's theorem. Why don't we go back to, and you can do that on your own if you like, and apply exactly the same technique in here. What if I have a curve in there, there's a vector field there. To calculate the work, we dotted these tangent vector, but why don't I, multiply the normal vector. If I have a curvature in there, if I have a vector field there, why don't I dot that to that? That would kind of measure and how many particles are, if you look at it as a kind of two-dimensional view, not complicated three-dimensional flow of particles. If it is just 2D stream of, water going in there in the same depth, something like that. And that's going to measure kind of number of a particle that's going through this net that is closed up. And then you will see that is the double integral over there and px plus qy. That will be the true analog of comparison between Green's theorem and divergence theorem. There's no cross and the subtracting like that. So I'll do that calculation, but it's very similar to this one. And I don't know what to call this one. This should be the divergence theorem. Again, 2D version. All right. Thank you.